Once you win a Nobel Prize, do you really need a side hustle? After detecting gravitational waves from the inspiraling collision of black holes billions of light years away, you'd think that LIGO could rest on its laurels. But no, scientists are trying to use this phenomenal machine to detect the most elusive form of matter in the universe, and that's what today's video is going to explore: dark matter and LIGO. Two great ideas that just might work better together. Let's go. The early universe was a very simple place. Primordial soup sounds complex, but it's actually pretty simple. It's composed of very simple ingredients: protons, neutrons, electrons, and add a pinch of neutrinos to taste, heat with billions of photons per baryon for about 3 minutes, and poof! The cosmic kitchen produced all the lightest elements on the periodic table. Everything out of this chaos eventually could form the building blocks of galaxies. Stars, after all, are formed from giant blobs of hydrogen that eventually start nuclear fusing together their protons to make helium, and so on. But how did those agglomerations of hydrogen know where to form? Well, they formed exactly where sufficient dark matter was to create enough gravitational field that these ordinary matter particles, the protons, could collapse and heat up and eventually have thermonuclear fusion begin. Now, we don't understand exactly the distribution of dark matter, so it behooves us to look with as many different techniques as possible. Because the hydrogen atoms were not evenly distributed, we infer that there must be gravitational overdensities caused by excess amounts of dark matter. So we want to learn as much about that dark matter as possible. Once the gravitational force causes gravitational acceleration, that creates enough energy to bind protons together to make helium. That process begins to run away exponentially. But it's not as simple as it might originally have sounded. With all we know about matter and gravity from our simulations, it's not possible to expect that just the amount of ordinary matter is sufficient to cause the gravitational collapse to begin in the first place. So we want to look for the effects of gravity from unseen matter, so-called dark matter, which we've known about since the 1930s. We know it exists, we know it's a known unknown, but we don't know what it is. We know it's a known unknown. From observations and simulations on all sorts of cosmic scales, from the clusters of galaxies that Zwicky first studied, to individual rotation curves of single galaxies that Veer Rubin and others observed, we know that dark matter exists on all sorts of scales in the universe. And we've talked about some of the observations on this channel in previous videos. Our paradigm for understanding dark matter suggests that each galaxy is actually surrounded by a vast halo of dark matter. This dark matter could be in the form of particles, or as we'll see soon, it could be in the form of what's known as a field, a dark matter field. These halos eventually overlap, and if you think about them as sort of Venn diagrams overlapping in three-dimensional space, eventually get these filamentary structures that form, and this is matched by simulations. So from the smallest scales of galaxies themselves up to enormous clusters of galaxies, such as the local supercluster, we know that dark matter tends to agglomerate in specific regions. That would mean that gravity would be concentrated along the most dense regions of the gravitational force fields produced by these dark matter halos. In particular, the Milky Way galaxy itself should have a copious amount of dark matter, and the Earth should be, in some sense, experiencing this dark matter as it moves around the orbit around the Sun, as the Sun moves around in its orbit around the galaxy, and as our galaxy moves towards the great attractor in the direction of the Virgo supercluster. So there should be a lot of dark matter right now. Look, there goes some right by you right now. Now, if you could see it, if you could look at it, it wouldn't be dark. So we have to look in other channels, other wavelength regimes, or perhaps in completely new techniques. And that's exactly where today's video focuses, no pun intended. Dark matter makes up about 30% of the universe's mass and energy. We know so little about it.
I don't even know who you are.
But it behooves us to look at as many different techniques and technologies as possible. And now the team using LIGO data has joined the hunt. There have been many studies attempting to pin dark matter on ordinary matter, just that is not brightly illuminated. In itself, by the case of, say, stars, white dwarfs, or so forth, or even super dense concentrations of ordinary matter that collapse to form black holes. Some of these attempts have focused on so-called macho.
You made a lot of promises to the macho man, didn't you?
Massive, compact halo objects, ordinary chunks of matter or perhaps little black holes that will distort the path of light rays from distant stars in a way that we can use to constrain how much dark matter there is. And in fact, we know there is painfully insignificant amount of dark matter in the form of machos to account for the missing matter that we know, the deficit between the ordinary matter, the kind of matter we're comprised of, and the dark matter that is suggested by the observation of the expansion of the universe, the Hubble constant, etc. We can only use gravity, perhaps, to learn more about dark matter's nature. John Wheeler said that space-time tells matter how to move. The curvature of space-time is what we experience as gravity. But matter tells space-time how to curve. So it's a complicated, interrelated, nonlinear process, this gravitational force field. So we'd very much like to know, on as many scales as possible, how gravity is affected by the presence of matter, dark matter in particular. Now, where does LIGO come into play? We've talked about LIGO with two of the Nobel laureates who received the 2017 Nobel Prize, my friend Barry Barish and my friend Ray Weiss, in previous videos. Subscribe and link to those videos. Now, new scientists, not affiliated with the LIGO team itself, but using data that's publicly available from LIGO, are on the hunt for dark matter signatures. But what does dark matter have to do with these massive things like black holes and neutron stars that LIGO is renowned to have discovered? Well, LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory, is one of the most sensitive instruments ever made, perhaps the most sensitive instrument ever made by human beings. It consists of these phenomenal interferometric arms, two of them separated by thousands of kilometers, one in Washington State and one in Louisiana. They're in the L-shaped configuration, is the most probable and profitable for detecting gravitational waves, which themselves have so-called quadrupolar distortions. We'll speak about that in future videos, how these detectors actually work. But today is not about the detectors, and it's not about gravitational waves either. It's about the basics of an interferometer. An interferometer is a device that goes back to the late 1800s, some of the most sensitive tools ever made for understanding the properties of light. It's made by shooting, in this case, two beams of light, two laser beams, at right angles, and measuring the pattern of interference as they come slightly into and out of phase with one another. They come together in a very complicated, expensive, and sophisticated device called a beam splitter, which splits and combines the light beams after they make their traverses through these 4-kilometer-long arms. Now, when the beams of light collide, they can interfere constructively or destructively, and that can be used for a variety of purposes. It could be used to measure the distortion due to gravity, a gravitational wave in this case, of one of the arm's length scales being modulated at the appropriate frequency or wavelength due to the presence of a gravitational wave passing through. Now, it will shorten or lengthen the path periodically, and this is what has been observed by over 100 such LIGO observations of black hole inspirals. But here we're not using them to detect gravitational waves. We're not talking about gravitational waves produced by dark matter or anything like that. We're using the complex and sophisticated and highly sensitive probes of the interference of light that can be measured uniquely with LIGO's sophisticated beam splitter. So these beam splitters can measure distortions over kilometers that are resulting from something far smaller than a nanometer displacement of these enormous optical path lengths. What LIGO uses is a huge, highly powerful laser.
A laser.
It goes down each tube, each arm of the L-shaped tube, in each of the two locations. And it's sent out in these evacuated vacuum tunnels, the biggest vacuums on Earth. They bounce and recombine in the beam splitter. This causes the interference pattern. We can predict very, very accurately what the beam splitter will see, if there are gravitational waves and if there are not. As of today, LIGO's recorded over 100 of these compact objects inspiraling together to produce gravitational waveforms which are successfully detected. So this method works exquisitely well, and LIGO understands exactly what these signals should look like in a wide variety of black hole merger masses. Now, most of the time, LIGO is not detecting gravitational waves from inspiraling black holes.
Can I talk to you for a second, please?
And so it was supposed that you could then use the so-called downtime when it's not observing, and it's sort of passively just waiting for a next black hole to inspiral with another black hole. You could use that downtime to actually probe the nature of dark matter. And here's how they did it. With the incredible sensitivity enabled by LIGO, researchers realized that the hunt for dark matter could commence in earnest using this new technique. In December 2021, physicists from Cardiff University, led by astrophysicist Dr. Hartmut Grote, used the LIGO setup to search for what is known as a scalar field dark matter. The idea behind this hypothesis is that dark matter is a so-called quantum field, a field endemic throughout the entire universe that gets stronger with mass and self-interaction. There are certain models in high-energy particle physics theories that predict such matter could exist. And it could explain the deficit between the observed matter that we know and the matter that we're made of and the matter we see in luminous objects and the total amount of mass energy we know exists. It's a huge deficit. In other words, in dark matter, there are multiple objects within a cluster, say a cluster of galaxies. The scalar field dark matter will pull them towards the center of mass of that cluster with a increasing and stronger gravitational force. Dark matter in this form would be weak enough to not affect things on human scales. Say, it wouldn't affect the effects of dropping an apple from the Leaning Tower of Pisa, but it would certainly be strong enough when you have enough gravitating matter in a cluster of galaxies to account for the effects, the gravitational effects that we know are present on individual galaxy size scales and on cluster size scales. Now, the team using the LIGO data didn't much look at the way that gravitational waves would affect the lasers in transit as the beam splitter and how it would be affected by the presence of dark matter. So they're not using LIGO to detect gravitational waves or detect black holes. They're using the sophisticated beam splitter and how exquisitely well the LIGO team, not affiliated with this group, the LIGO team understands its sensitivity and has modeled its performance. The way a beam splitter works is that it reflects half the light that comes in at a right angle and lets the other half pass straight through. You can see something like this happen when you look at glare on a window. Any transparent surface will let some light in and reflect some out, with the amount of each being dependent on the angle and the wavelength of light and the surface preparation of the beam splitter. What Dr. Grote and his team hypothesized was that the interference caused by scalar dark matter would actually cause the atoms in the beam splitter to move subtly out of place, which itself would cause an interference pattern. He's using it as a very sensitive detector of quantum fields, a new kind of dark matter. Looking at a vast amount of data, the team found no evidence that scalar dark matter fields were active. This doesn't rule them out completely.
Just because you can't prove it doesn't mean it's not true.
But it does mean that scalar field dark matter would have to be about 1,000,000 times weaker than previously thought. It also rules out a lot of major subsets of scalar field dark matter models. And it rules them out as contributing very much to estimation of how much dark matter they can contribute to. It's worth noting that the team doesn't believe that scalar field dark matter is the only kind of dark matter or form of dark matter to exist. If that were true, it would mean that we really have no clue as to what dark matter is. It's just another candidate for dark matter. There are other candidates. We mentioned machos earlier. There are other candidates, such as so-called weakly interacting massive particles, or WIMPs. I've talked about neutrinos on this channel as being the only form of dark matter that we know exists. Neutrinos, after all, suffuse the universe. They have masses, albeit quite tiny, and they only interact weakly and gravitationally as far as we know. There could be other particles like this that either don't interact with the other three forces of nature, the strong force, the weak force, the electromagnetic force, and these forces could be particles or they could be fields that interact, and we just don't know. There are other candidates, in particular, candidates called axions or dark photons, and the more that we investigate, the more we're going to learn about these types of matter. And I'll talk more in future videos about axions and about dark photons, such exciting candidates that we're just now getting sophisticated tests of, both on particle physics experiments on Earth and also looking astrophysically with tools like the Simons Observatory and other experiments. We're clearly at a point where both scalar field dark matter and WIMP dark matter have failed to be shown to exist with significant evidence. Neither can be ruled out entirely, and it's entirely possible still that another type of dark matter exists on a scale too large or too weak for us to detect. The team isn't discouraged though. The search has been called a fishing expedition, and we all know that you never stop just because you didn't catch a fish.
Give the Chief a hand, will you?
So it's a proof of concept for now, and it's a very, very special and encouraging one to continue looking for old particles with new technologies. So, the experiment proved that LIGO isn't just good for detecting black holes. It can be used to constrain models of dark matter and even modifications of gravity itself. What's exciting to me is that these researchers didn't request to build an entirely new particle physics detector or some new type of telescope or technology. They're using existing telescopes, in this case LIGO, and even existing data. They didn't even have to run LIGO for a longer amount of time to collect these data. It's an exciting but preliminary first step. The team has already begun making plans and doing preliminary research into other dark matter candidates, such as axions and dark photons. We'll discuss those in future videos. There's even more that can be discovered, and attempts to possibly measure quantum gravity, large-scale kilogram chunks of dark matter, all to try and understand the progression of how our universe came to appear the way it does, with luminous structures sprinkled on top of invisible dark matter halos. All of this is allowing us to get more light on dark matter, understand the nature of gravity, and in turn, understand how matter and space-time itself came to be. Check out this video that I made, What is Dark Matter? And make sure to subscribe to my channel so you don't miss an episode.